Okay, so now here's the problem then, is how do we measure all the things that we make? Micrometer, nanometer, how do we do that? You can't just look at it and say, oh yeah, that's about 150 microns deep and 25 microns wide. I know that. So that's how I knew that. So that's the challenge. And that's the whole process of metrology, trying to figure out how well you did in making all the structures that you've developed. And that's can be a very simple or a very arduous process, depending upon the scale of the structures that you're making. And I'm okay. So let me tell you, I'm going to go through this pretty quickly because of time. And if you have any questions after you leave, you can always email us if you want to have some follow-up discussion on things. That goes with everything that you heard today. I know everyone's head is spinning because you've heard so much material, but we have, over lunch break and other times that we can freely discuss things, and that I would encourage you to do that. Okay, so there's a lot of different ways to do metrology. Metrology is basically measuring the physical size of the structures that you make. That's basically what that is. And there's a whole slew of techniques to do that. One is doing contact, where you actually have a probe or a stylus that runs over the structures that you make. One is called optical or non-contact profilometry, and that's using a type of microscopy process. And actually, you'll use one of this in the lab when you start working, making your device. And you've already seen this, scanning electron microscopy. That's a really nice tool in order to measure metrology on the nanometer scale, and atomic force microscopy. So this is contact profilometry. All right, nothing really complicated about this. You take a tip and you run it over the surface, and it goes up and down to follow the contours of that surface. But there's some things that you should always be aware of. So it looks at the height of that stylus, and from that it deduces the morphology of the surface, the roughness. And I'm just going to call your attention right here. Look right here. You can already see a problem. The stylus is so big, it doesn't fit into that small crevice. So it's giving you a wrong answer. It's not giving you the true representation of that surface because of issues with tip effects. So you need to keep that in mind whenever you're using contact profilometry. Okay, and then this is just giving you an idea of how that works. You can see here the detecting point. It's moving across this object to kind of determine what it can do in terms of measuring the surface morphology. The stylus radius can range from 20 nanometers to 50 millimeters, so it has quite a large dynamic range. Most clean rooms do have a contact profilometer in them to do these measurements. All right, that's kind of a common tool, and the reason for that is not very hardware intensive, and it can give you results fairly quickly. And then this is just a common output from a contact profilometer. And you can see here, you're looking at the height of a particular pillar that was made by using your favorite fabrication process. And these will work on anything. Glass, polymer, silicon, anything it'll work on. No problem. PDMS as well. Optical is different. I'm not going to talk about interference microscopy, just confocal microscopy. So I think that's the next slide. Now I'm going to come back to this. Yeah. All right. Everyone has sat in front of a microscope before. And what does a microscope do? It takes light and it focuses it down to a very small spot using a microscope objective, and then raster that spot across a sample. And a common way to do that is using like a fluorescence microscope. So when that beam of light that's impinging upon the sample hits that fluorescence, it lights up. So you see differences in the fluorescence intensity, and that's called a fluorescence microscope. This is a little bit different. You can see this here. It's some laser that's being focused down onto this surface. And then what you do is you raster this laser beam over that surface from which you want to determine the roughness or measure the metrology. So look what happens then. Some of that light is reflected. It goes through what's called this beam splitter and impinges upon this detector. So the amount of light that you measure will give you an indication of the topographical features on that surface. And there's one unique thing with this. There's called these pinholes here. And basically what that does, those are called confocal pinholes. And basically what that does, it increases the resolution. So when you're, just like we saw for the contact profilometer, the lateral resolution in the XY plane is determined by how small the tip of this profilometer is, as well as the step resolution, because this has to scan over this surface. The Z resolution is primarily determined by how small a measurement or displacement you can measure on that stylus. And it's not so different here. There's XY, where you scan that laser beam over the surface. That'll determine the lateral resolution, the XY plane. The Z direction is determined by the amount of scattered light that you measure onto this particular detector. Okay, so I'm going to skip this one, but Brian, this gives you the answers of that chip I gave you. So you can see here, this is called a confocal image of that particular chip. And it'll measure this even, this is on the molding tool. This is the molding tool, has the what's called the reverse polarity of the final structures we want to make. So we want to make structures that are channels, they're troughs. So the molding tool has the reverse polarity. So it has protrusions in it. And these protrusions define the pattern that we use in the molding tool to create in the injection molded part. So you can see this right here. They're about 150 microns deep and 25 microns wide. And it does, I mean, this is a pretty image to look at. So this is not using fluorescence. It's using scattered light that's generated, reflected back off of that surface that's measured by this detector within the microscope, this confocal microscope. And what's really nice about this is that it's not limited by the size of the stylus or the tip of that stylus that runs over the surface. And there's no contact. It's just photons impinging upon that surface. This is actually quite interesting here. So you're looking at the stylus contact profilometry versus optical profilometry. And if you look at this 20 micron pitch, that means that the spacing between these structures is extremely small. You can see what that topographical features look like with the stylus because it doesn't fit into this small group. But with the optical profilometry, it doesn't have that problem. Not at all. So it's not limited by the size of the stylus that you would use in contact profilometry. Okay, but so what about optical imaging or optical metrology? What is its resolution? What is its limit? And you know what? That's determined by the wavelength of light that you're using in the microscope. So in this microscope here, it's using a 405 nanometer laser, violet laser. And the reason for that is it really gets the resolution in the XY plane and even the Z, XY plane, quite favorable. So usually about lambda over 2, or lambda is the wavelength, will ultimately give you the resolution, which is about 150, 200 nanometers when you're using a 405 nanometer light. And there's all sorts of physics that help you describe where that comes to pass, but I'll forego that now. All right. Scanning electron microscopy. Well, Dr. Park already kind of explained that to you already, believe it or not. The only difference is instead of using an ion, you're using an electron. Okay, ion versus electron. What are the differences between an ion and an electron? Well, ion's going to be heavier. An electron's going to be very, very lighter, so to speak. So what does that mean? Well, when I take an ion like gallium and I accelerate it and impinge it on a surface, it's going to blow material away, ablate, just like Dr. Park talked about. Electron, not so. It won't do that. So it'll do much less damage on the surface than an ion. But the imaging modalities are actually quite similar. Dr. Park said that ion beams will do imaging, but you do have to live with a little damage of the surface, whereas electrons, you don't. So just think about this for a little bit, though. What is necessary? I mean, you saw a lot of SEM images, whether you knew it or not. What is required of the material in order to image it using a scanning electron microscope? Does anyone know? Does anyone want to guess? Shaquila? Yeah, it has to be conductive. So let's say I made a really nice little widget in a plastic, and I want to take it to the SEM to see if it adheres to what I designed. What do you have to do first? Plastics are not conductive. You have to make it, even PDMS is not conductive. You have to make it conductive, so you have to put on a very thin layer of some conductive material, like platinum, in order to make it conductive to image it with the electron microscope. And with the optical profilometer and the non-contact profilometer, that's not necessary. You don't need the surface to be conductive. But electrons, you can focus to a much smaller beam size, much smaller than you can with light. So what that basically means is that your resolution in the XY plane is going to be much improved with an electron microscope than you're ever going to get with an optical microscope, like using the optical profilometry. So yeah, a lot of these things are very similar components to what you saw in the ion beam instrument. In fact, actually, you can buy instruments that are dual purpose. They'll have an ion beam column and an electron beam column on them as well. And I think one of the instruments that Dr. Park showed was a dual beam instrument. It had an ion and an electron beam on it. And the things that you need to just remember with electron microscopy, scanning electron microscopy in particular, is that you're looking at primarily backscattered electrons or secondary electrons. And we could talk for days about how those are generated. But I'm going to cut to the chase here. The other thing that you have to keep in mind is that sometimes, just like Dr. Park showed, the ions will penetrate into the substrate. The electrons will do the same thing too. And that will affect the quality of the image that you get out of the scanning electron microscope. I'm going to skip this. And remember, I showed you two things that are the primary sources of the electron image, the scanning electron microscope image, the backscattered electrons and the secondary electrons. And the main thing is for everyone to remember just very quickly is that you want the best possible image that you can attain. So do you get better imaging with the backscattered electrons or the secondary electrons? And that's a good issue to kind of deal with. And this kind of tells you that. But if you look at this is the backscattered electron image. This is solder on a circuit board. And the secondary electron image is giving you a little bit different types of information that you can get from the backscattered electron image. So the bottom line is the electron microscope will collect both images, and sometimes you can compare and contrast both of those images to get contrast features that you wouldn't normally see with just one or the other. So what is the ultimate resolution on a scanning electron microscope? That's a hard one to kind of answer because it depends upon the electron microscope that you're using. But a lot of the features that we showed, and if you looked at some of the things that Dr. Park showed, structures as small as 5 to 10 nanometers, even 3.5 nanometers, those were imaged with an electron microscope. So you're well within the resolution limits of the electron microscope. There's no need to go into anything any lower than that. So usually the things that I've seen in the literature with people doing nano patterning, sub 10 nanometers is probably where we would be. There is some work. Yeah, that's what I would say. There is some work. There's a group that now is generating structures that are even around 1 nanometer or slightly below. Okay. And this is just to show you all the physics associated with charging. We alluded to this. And this is actually quite interesting. You can see here, negative charge buildup on the specimen can actually provide issues with the quality of the image that you generate. And you can see that here, coded versus uncoded. Again, I apologize, I'm going through this kind of fast. The last thing that I just wanted to briefly touch on is atomic force microscope. All right. What is the difference between atomic force microscopy and contact profilometry? Nothing, really. Not a big difference. The only difference is in this is that, and I'm going to show this, is that you're using a much finer needle or probe. These probe sizes can be less than 10 nanometers in size, where the contact profilometer, I showed you 20 is about as small as you can get, and that's rare. They're much larger than that. So the bottom line is that you have less artifacts due to probe effects, tip effects with the atomic force microscope. And that's basically what this looks like. These are silicon nitride membranes, silicon nitride structures with these tips machined onto them that are typically, again, like I said, less than 10 nanometers in size. So these do a very good job of imaging fine structures that you can use for non-conductive materials. So like plastics, you can easily use AFM to image that with an AFM without requiring the need for coating it. And if you're looking at something that's several nanometers in size, and you have to put a coating on it that's several nanometers in thickness, then it's not going to work. So this obviates the need for putting those conductive coatings on it because there's no charging effects that's on here. And let me just point out one thing here. You can see what happens. The measurement process is actually quite simple. So you're looking at the deflection of this tip as it's going over this rough surface. If I shine a laser on that, it actually generates a pattern on the photodiode that's indicative of how much that tip is bending. And that'll give you an indication of the topographical features of this surface. And the sample is put on a piezoelectric scanner. It gives you very good XY resolution. And you'll see one of these in the clean room. There's an AFM in the clean room. We have one in our lab too. All these metrology tools that I'm alluding to actually are either in the clean room or in the lab upstairs. And challenges with AFM is the scans take much longer than SEM, and there is tip artifacts, but they're looking at molecular structure is actually quite intriguing using AFM. So 3D map a surface, calculate surface roughness. There's all sorts of forces that you can measure that we could really talk about quite extensively. Okay, but again, there is tip artifacts here you just have to be aware of. If you're looking at really, really deep structures that are narrow, you will have tip artifacts, even for something that's very small, like less than 10 nanometers in size. So you just need to be aware of that. Okay, I went through that quickly to get us a little bit back on schedule. I apologize for that. But again, if you want to know more about the metrology, please let us know. And you will be doing some metrology on the device that you're making as part of the laboratory process. And I think you're going to use the confocal microscope to do that. Correct, Maggie? The confocal microscope? Yeah. So you'll actually get a chance to use that and see how that works. I think you'll enjoy seeing that.
The optical profiler, yeah.
Yeah, the optical profiler.
We have time maybe for one question. Anyone?
Okay.
Okay.
Here's the question you should ask. Well, which should I use? Should I use AFM or should I use scanning electron microscopy if I'm using contact profilometry if I'm doing microstructures like 10, 20 microns? Oh, heavens, don't use AFM or what was the other one? SEM. Ridiculous. That the size of the structure that you generate will predicate which profilometer technique you should use. For 10, 20, 30, 100 micron structures, contact profilometry is the way to go. If you're measuring something of intermediate size, like half micron all the way up to about 10 microns or so, then the confocal way is a beautiful way to go. If you're measuring sub 10 nanometers, AFM or SEM is the way to go. If you don't want to worry about charging effects and putting a conductive layer on top of it, then I would do AFM. And some of this is predicated also on the tools that you have access to. So everything that we talked about is here. And I just stress this a lot, is if you need to do some structure manufacturing or fabrication, but you have no way to check out structures with appropriate metrology, you can see us and we can help you with that. That's part of our job. It's part of our NIH center. Okay.
Thank you so much.
Thanks, everyone.